Okay, thanks very much for the introduction, Julia. And I've really enjoyed the talks here so far. I'm looking forward to the rest. And I'm also looking forward to taking a couple of weeks sabbatical from life to actually read this IPCC report. I mean, actually get past the summary for policymakers. As Julia mentioned, I mean, the global water cycle it's kind of seeped through the whole IPCC report because, of course, it's got a number of drivers, a number of importances, and of course it's of intrinsic importance to societies and ecosystems. So whether it's delivering too much fresh water at one time or delivering not enough, they're profound impacts on society. And on the other hand, it's a blooming fascinating subject as well. I mean, how does the global water cycle change? And I'm not going to do it complete justice. I'm going to inevitably focus on areas that I've looked into more detail. So in particular, looking at water vapour and precipitation changes. But you can always see some of these driving forces for the very basic driving forces for the global water cycle, looking back to the studies of Manabe in the 70s, John Mitchell, of course, as well, in the 80s, did some nice work on it. And I think I'm going to present today some of our current understanding, some of which is in the IPCC latest report, and some latest work which may or may not be controversial. I'm sure Kevin will pick me up later. So, right. So to start off with, I'll pay homage to the IPCC report with three diagrams. I think this is the pointer. So in terms of answering the question, which was, how confident are we in the response of the global water cycle to climate change? So on the one hand, we're very confident that precipitation will increase. According to the projections, vast areas of the global land will experience an increase in precipitation intensity. This is actually 5-day maximum precipitation. But at the same time, there'll be large areas which will experience less soil moisture, less precipitation, and a complex relationship between some of these metrics and what actually matters for people. So there's a huge human component to drought as well, which you can't ignore. And on the other hand, we've also got, putting these two together in some semblance, you have this diagram, which looks a bit of a mess, but we're kind of starting to understand some of these signals of the wet regions becoming wetter to first order, some of the dry subtropical regions becoming drier, and some of the high latitude regions becoming wetter. And again, the moisture convergence regions tend to become wetter, and the moisture divergence regions tend to become drier. Then you get onto the more thorny issue of, what happens to my river catchment? And you really run into a problem there because, of course, it's really dependent on how the atmospheric circulation changes, and some aspects of that are very uncertain, and how exactly the jet stream shifts, how exactly monsoon regimes shift. But I could argue you do get some insight from some of these large-scale factors, which I'll talk about. Here's just a diagram. It's not all the models, but some of the models from the RCP and historical scenarios, looking at how does global mean precipitation change as time goes on. We've got the past here, some cursory observations from the GPCP and projections from RCP 8.5 and RCP 4.5. Now, the first thing to notice from this graph is actually, in terms of global precipitation, we've hardly started, more so perhaps than temperature. So we've barely even gone out of natural variability. But, you look at these changes out to 2100, it ranges from anywhere from, say, 3% up to 12% for these models in question. So there's a huge range. What explains this range in global precipitation change? So, we know that global precipitation will rise with warming, and that can be traced back to some fairly basic physics, in terms of the fact that if you're thinking about the energy balance of the atmosphere or the energy balance of the surface, then as you raise the temperature, assume that you're getting radiative convective balance, the moist adiabatic lapse rate is to first order retained, then that warmer atmosphere is able to radiate more effectively. Now you also get changes in water vapour, which kind of go one way and the other. A paper by Mike Prevedi, it's quite nice that actually the low level water vapour has an opposite effect to the upper level water vapour in determining how the atmosphere radiative cooling changes. But to first order, it's just the fact that a warmer atmosphere radiates more efficiently, and you can plot a bunch of observationally based estimates and models, and this, especially the clear sky long wave radiative cooling, enhances substantially with warming. And if you keep that radiative convective balance in mind, then this is a very strong constraint on the fact of why precipitation increases in a warming world. This is offset by solar absorption. There's some cloud effects which can go either way. And what we'll talk about now is there's some other effects on the atmosphere radiation balance and surface radiation balance that actually are independent to each individual radiative forcing that also has an impact. More is written on this, Miles Allen, William Ingram's paper, of course, and we did a review with Paul O'Gorman as well on this. So this is the nicest diagram, I think, that Tim Andrews produced during his PhD thesis. And it shows for two different scenarios, a 2 times CO2 forcing scenario and an increase the solar constant for a similar kind of radiative forcing scenario. Increases in precip, increases in temperature. And this is the Hadley Centre slab model here. And firstly, you can see actually that in the solar case, the temperature doesn't rise quite as much as in the CO2 case. So some of this is this radiative forcing efficiency effect. But despite that, even though you get smaller warming in the solar, you actually get a bigger precipitation response. And this is very nicely understood in terms of plotting out, I think it's the decadal average values as you go out to equilibrium. And what you have is that basically, as the temperatures rise, you get a smooth increase in precipitation with warming in both cases. They're both following the same line, and that's based on this increases in the radiative cooling of the atmosphere, which is very well understood in terms of the radiative transfer and the thermodynamics. Now, the difference between these two is what kind of happens in the very early stages of these simulations when you increase solar or double carbon dioxide. In the solar case, it's not a big effect, but in the CO2 case, you get this big drop such that at zero temperature change, you've actually got a decrease in precipitation. And that is basically because the CO2 forcing is effectively, that heat is being dumped in the first place in the atmosphere. And the most efficient way to transfer that energy from the atmosphere down to the surface is through adjustment involving radiative transfer adjustment, convective adjustment, such that this energy is put down into the surface by reducing evaporation and reducing precipitation. So that's why you get this rapid reduction. Now, in the real world, of course, CO2 is gradually rising, but you've still got this effect going on. And that can go a long way in kind of explaining the effective response of the climate of precipitation to the different radiative forcing. Now, if you want to you can play around this with a master student or PhD student and come up with a very simple model such that precipitation is equal, you're equating the energy balance of the free troposphere, basically, above the boundary layer. And you can say there's this warming term that's simply related to the radiative transfer, and this extra term relating to the forcing. Some forcings dump their energy in the atmosphere, others, like scattering aerosol, the forcing is felt immediately at the surface, so you don't get a rapid adjustment. So each of these F values is distinct for different radiative forcings. So this shows the F delta F, so this is the increase in radiative heating due to the different forcings. So we have CO2 heating the atmosphere, black carbon, well-mixed greenhouse gases. This is just an illustration, it's not very accurate here. So these are all reducing precipitation, and yet the warming in response to these radiative forcings is increasing precipitation. So what you can see basically is you have a fast response going down like this in response to this increasing radiative heating, and you have an increase in precipitation because the planet is warming in response to this, and there's volcanoes going off as well which don't have a big effect on this atmospheric heating. And you get this overall kind of balance in this very simple, this is just using a 2-layer simple diffusion ocean kind of model. So it's not realistic, it's just kind of an illustration. But it kind of goes a long way in trying to understand what's going on, and it actually says why we shouldn't expect too much of a global precipitation response so far. But increasingly, as you progress out into the future, where warming really starts to dominate, then the warming effect will win out, and that's why you do get the overall increase in precipitation going out to 2100. This has got some quite interesting implications for the transient climate response. Again, going back to some of Tim Andrews' papers with Piers Forster and others, he showed that when you do the same plot of increasing CO2 gradually, you get this rise in precipitation up to the point that you then stabilise CO2, and then the planet carries on warming because it's not in equilibrium, but you get a kind of ramp up in precipitation then, because suddenly you're removing this offsetting effect from the rising CO2 levels. Paley Wu, for example, has done other analyses just like this that have shown a similar thing. And he's done an updated paper, which was quite nice, in Nature Climate Change recently, where he showed how precipitation and temperature are varied in the different historical runs using different forcings. So, for example, here's the greenhouse gas only forcings going up there, and here's the natural forcings only, and you actually get a stronger response between precip and temperature here because it's primarily scattering aerosol or solar things which don't have this big adjustment, whereas greenhouse gas has a weaker hydrological sensitivity because of this offsetting effect from greenhouse gases. Now, if you add in the sulfate aerosols, which don't have a heating effect in the atmosphere very much, apart from the absorbing black carbon and things like that, what happens is that you've got CO2 rising, so even though temperature's not changed here in the kind of mid-20th century, you're getting a reduction in precipitation because of the CO2 still rising, and then towards the end of the record, then it's moving back up again, up this trajectory here. So yeah, I'd recommend kind of having a look at that. It's a good way to understand how the interplay between sulfate aerosols and greenhouse gases has gone into producing these rather funny and small changes in precipitation so far. And again, that's got implications for geoengineering as well, because if you're offsetting the heating effect from carbon dioxide using solar radiation management, for example, you're again having these big effects on the hydrological cycle. And now we're going to turn on to another aspect, which is the role of water vapour. Again, another central area of confidence that we know the Clausius-Clapeyron equation. We know that the basic relationship of saturation vapour pressure rises with temperature. It rises much more at colder temperatures, so you get a bigger response high up in the atmosphere, a slightly bigger response at the colder polar regions, but mostly near the surface it's around 6 to 7% per K. And this has implications for the hydrological cycle. Now this just shows some observations of surface temperature changes, so this rapid period of warming, this kind of slowdown period up here in the most recent decade. And this shows water vapour changes as well, based on a bunch of things. So we've got, in grey, we've got the AMIP simulations, so we're giving them the observed sea surface temperatures. We've got microwave data filled in with reanalyses where they don't measure over the land, and era interim reanalysis. Now, there's a few points to note from here, of course. One is this very strong covariation in water vapour. There's much more water vapour in 1998 when there's warmer temperatures. Simple Clausius-Clapeyron relationship playing out there. Another thing is that comparing the HAD-CRU-H surface-specific humidity variability with the microwave blended with the reanalysis estimates, you get very good agreement between the blue and the red. So these are very independent, apart from over land, estimates showing that the surface-specific humidity and column-integrated water vapour are very strongly related, very strong agreement. So we have very strong confidence in this water vapour changes, interannual variability, and also the trend. So in the warming period, you have a trend of around 1% per decade in water vapour. A final point is the reanalysis era interim gives almost no trend or a downward trend in water vapour here and an upward trend there, which actually is mentioned in the D et al. Paper that introduces era interim. And they note you can't trust the reanalysis global scale changes in the water cycle because it's simply not balanced. Maybe future reanalyses which are balanced, if a climate reanalysis may be more balanced, maybe you can do something more. But the changing observing system means that you can't use reanalyses to look at trends simply in this way. This has implications, this rise in water vapour with temperature has implications for extreme precipitation. Put simply that, if your large-scale rainfall event is relying on sucking out moisture from a very large area around it, if you're simply increasing the water vapour in that area of convergence of moisture, then you can, by first order, simply expect that precipitation intensity will rise along with Clausius Clapeyron, along 7% per K. We've looked at interannual variability, and you get some semblance of this. If anything, it seems to have a larger sensitivity in the observations, although there are some fairly hefty uncertainties in the observations themselves. There is some evidence, observational and theoretical, suggesting that you could get some amplifying effects, that in fact you're converging more moisture, or in an individual storm you're releasing that extra latent heat. You could invigorate that storm and make the intensity go above Clausius Clapeyron. That's one possibility. But over a larger scale, of course, all that extra heat will be stabilising the atmosphere. So there's kind of a very strong interplay between the time scale you're considering and the space scale as to the exact relationship, I think. But there's some really nice work, I think, by Paul O'Gorman, where he put a bunch of models trying to relate the interannual variability sensitivity of extreme precipitation to the climate change response. And he found there's this very nice linear relationship between the interannual response and the climate change response. And he's plotted over the observed estimates as well, which kind of suggest, again, a value above Clausius Clapeyron of around 9-10% per K in extreme precipitation. So that's quite a nice result, and it'd be good to see if that can be reproduced with the most recent models and the most recent observations. Another thing we've been interested in looking at is, rather than, we know that climate models do struggle a bit in terms of intense rainfall because they're not actually simulating these individual clouds. So can we actually bypass this by actually looking at the events, so the flooding events or high river flow events, and relate this back to the very large-scale precursors of the events? So we've done some work looking at for example, this is the 2009 flooding event in Cumbria, and this just shows column water vapour from era interim, and arrows are plotted where there's very strong moisture transport. So that's basically just the wind blowing the moisture along. And if you're raising this over mountains, then it quickly starts getting squeezed out, partly through direct squeezing it out, but also the seeder-feeder mechanism, where you get extra rain that is then seeds more rain in the cloud. And so we've done some work trying to look at, how do these, trying to detect these kind of warm conveyor belt, atmospheric river type, strong moisture transport episodes that are linked to the flooding events. And we're looking in the climate change runs, we find that basically assuming a Clausius Clapeyron response can explain quite a large part of the increase in these atmospheric river events, or the number of them, or the intensity, but not all of them. And that again brings in the point that these actual events in the warm sector of a depression are obviously very dependent on the ongoing dynamics. How do they evolve in a warming planet? How does the jet stream shift in a warming planet? So that these things also start coming into play, as well as the simple thermodynamics. So then you get on to the how does he reconcile this heavy rainfall going up with water vapour and the large-scale precipitation rising much more slowly, along with the energy balance constraints of, say, 2%, 3% per K. So somewhere else there's got to be either a lesser precipitation rise or even a decrease. Can we see this? Well, firstly, can we understand it? I mean, you can understand it to some senses from a simple moisture balance argument, such that if there's moisture flowing into a region, and big assumption, you assume there's no change in the atmospheric circulation, then if you increase the amount of water vapour, then you have more moisture convergence in the moisture convergence regions and more moisture divergence in the divergence regions. And from a very simple moisture balance perspective, you can say, well, that means that P minus E patterns should amplify. So and you could kind of reproduce this. Held and Soden did this, where they showed, roughly speaking, the moisture convergence regions had increased P minus E, and the divergence regions had decreased P minus E. And of course, this has implications for ocean salinity, such that the salty regions get saltier and the fresh regions get fresher. And that some of this seems to have been observed based on the work by Paul Dirac, for example. So some tantalising evidence. But again, these convergence and divergence regions have the annoying habit of moving around spatially. So you can't be too sure that one exact region is going to follow its original trajectory. So, can we see this in terms of the precipitation record? So this actually shows some work we did with Chun-Li Liu, Well, we just simply split up, here's the tropics between ocean regions and land regions, and looked at how precipitation in the wet regions and the dry regions, defined as the 30% wettest precipitation grid points versus the 70% driest grid points. And you can see that you do get this strong signal of the wet regions becoming wetter in the RCP 4.5 model, and the dry regions getting drier. And interestingly, you kind of see this in the GPCP observations as well, although and this is the GPCC surface record, you get much bigger variability, although we seem to find that this correlates quite strongly to decadal changes in ENSO, which was quite interesting. So there's a big discrepancy between the models and the observations there. But there is some semblance of the fact that this wet get wetter, dry get drier is borne out by the observations, however uncertain these observations are. And of course, going over the ocean, you really run into trouble with the microwave data. Before 88, there wasn't really any microwave precipitation data, so we didn't include that. But even in this latter period, if you talk to a microwave retrieval guy, he or she will come out in a cold sweat when they talk about this. So you can't say anything much about microwave precipitation. We don't know. Whereas perhaps they're being a bit too cautious about their data. But certainly the variability is much bigger than we get from the models in the dry regions, at least, over the ocean. Yeah, and in terms of the ENSO, the difference between ocean and land is very dependent on whether it's El Nino. If it's El Nino, you'll tend to get less rainfall over the land, and La Nina, you'll get more rainfall over the land. So you can get massive interannual variability between these two, in particular over land because it's a smaller area, simply because whether the observations have a El Nino or a La Nina compared to the mean of the models, which of course by definition shouldn't have either because it's a mean. Going on to some more controversial stuff. So there's an expectation that the Walker circulation will actually decline as the global temperatures rise. And this is partly can be thought simply in terms of if precipitation is simply thought of as a mass flux of this moisture out the boundary layer and up through the ascending mode. If precipitation is rising at 2% per K and moisture is rising 7% per K, then simply speaking, this mass flux should decline. So simply you should have a declining Walker circulation. Another aspect to this is the fact that if you keep a moist adiabatic lapse rate, you're going to increase your static stability. And so if you're thinking about the aspect of the circulation that is driven by radiative cooling, then in fact, because of this increase in static stability, you'll have to sink the air less to get the same heating effect to counteract additional radiative cooling. So effectively, that's another argument why you can expect a decline in the circulation. Some nice discussion of this actually by Mark Zelinka and Dennis Hartmann as well. And I think Robin Chadwick is arguing that actually this effect should counteract all of this wet get wetter, dry get drier, if I remember rightly. He can correct me on that. But I think to a certain extent this doesn't completely balance. So you do still get, as I showed in the previous plot, you still do get this wet get wetter, dry get drier. On to more controversial stuff. This is a paper I really liked, although, and talking to a few people, there's been some sceptical murmurings, in particular at the Met Office, about these results. I haven't spotted what was wrong, but it was quite a complicated paper. Anyway, Sondri and Bonnie did a very nice study, which I think just about made it into the IPCC, if I remember correctly. And they note that there's actually, as well as being a fast and slow response of the global precipitation to radiative forcings, there's also a fast and slow response of the Walker circulation as well, such that you get this slow thermodynamic response that the wet regions get wetter and the dry get drier as the temperature rises, simply because of this P equals MQ kind of constraint. But on the other hand, the fast response is reducing precipitation on its own. So if you reduce precipitation, yet you're increasing moisture, then you again have to reduce the mass flux. So again, they find a fast response of slowing of the Walker circulation. In essence, they're kind of arguing that this fast response to CO2, this decline in precipitation, is primarily felt through the Walker circulation decline. Again, there may be some problems with the method that they produced. Also to notice, Vecchi et al., for example, show some observations of a decline in the Walker circulation, but linking back to Jocham's talk earlier, there's some interesting results that actually in the recent decades, the Walker circulation seems to have strengthened, such that the kind of more La Nina-like state has sent a stronger Walker circulation in contrast to what we might anticipate. Another really interesting area of research, I think, relates to aerosol, and the fact that aerosol has this huge effect, in particular on shifting the circulation patterns. So Huang and others, they showed that enhanced cooling due to aerosol in the northern hemisphere alters the contrast between heating between each hemisphere, and that can actually shift this whole Hadley cell. And they argue that quite a lot of the change in Sahel rainfall can be explained by this changes in Sahel in northern hemisphere cooling due to aerosols. There's been other nice papers, Martin Wilt, the global dimming up to the 80s and the reversal brightening thereafter, which seems to have also reversed the Sahel rainfall. Jim Hayward has done some nice work showing volcanic aerosol can have a similar effect depending on if the volcano is in the northern hemisphere, in the tropics, or in the southern hemisphere. Some nice work by Bolosina looking at sulfur aerosol and the effect on the Walker and Hadley circulation, and possible links to the Horn of Africa drought as well in terms of the anthropogenic aerosol effects. So there's some really interesting work to be done with the aerosol. Okay, my final point then is, on top of this, I mean, aerosol can help, I think, in understanding some of these circulation, force-driven responses to circulation, but there is an inherent randomness as well involved in that it's all very well saying, we get these large-scale patterns in precip, but what about the local scale? You can get some semblance of seasonal responses in precipitation, but they're very dependent on how the jet stream shifts in a warming world, in a change in the Arctic ice, in a change in the temperature gradients, changes in monsoon systems. Should also mention that I think the big step forward from Scott Power's paper is to mention that there's actually large regions where there was uncertainty in precipitation response, where we're kind of certain that precipitation won't respond that much compared to natural variability. So that's kind of a step forward in this IPCC report. And finally, of course, there's the land surface and ocean atmospheric feedbacks, which really affect the local scale circulation responses. In particular, where the ocean warms up the most, where the land warms up the most is really going to determine where the circulation kind of shifts to. So I think there's a lot of new stuff that can be done in understanding a bit more carefully how regional responses in an atmospheric circulation and the regional responses of the water cycle will progress. I'll rattle through this very rapidly. Observing systems are a problem. We can't monitor changes in precip and radiation adequately yet. The regional predictions are a problem. Will extreme precip outpace Clausius-Clapeyron? There's evidence to suggest it will. Implications for geoengineering. Interesting question. Should we expect the hiatus with increasing CO2 and flat temperatures? That should have an effect on the water cycle? For example, some semblance is that you should expect less water to be transported over the land because the ocean temperatures haven't risen, but the land temperature rose a little bit. And finally, just to reiterate that point, that the aerosol is a really key ingredient here, understanding how the regional circulation shifts in response to aerosol, and perhaps we can get further in understanding how the patterns of temperature change really affect the regional response of the water cycle, and that's where I'll end. So, thanks.
Thank you, Richard, for a very comprehensive report on the latest thinking and indeed posing, I think, some nice questions for future research. So I'll take, we have 15 minutes for some questions. So, questions. Well, we'll start with Kevin.
Hi, Richard.
Hi.
Hi, Richard. That was actually quite a nice talk, but I thought you maybe
So damning with faint praise, yeah.
On your opening slide, where you showed the overall changes, especially in soil moisture, I was surprised that you didn't mention the increase in evapotranspiration, and which is a big factor in the drying of soil moisture. It's not really a precipitation effect, and so that was one omission. The other thing I would like to point out is the Chapter 14 of the IPCC report, which dealt with regional aspects and monsoons. And there's quite a nice paper that was produced by the Chapter 14 authors, led by Quito et al. In JGR in 2013, that looked at the changes in monsoons, and it actually encapsulates a lot of what you were talking about, showing that there's an increase in the convergence of moisture because there's more moisture in the atmosphere, but there's a slowing down of the monsoon circulation, but the convergence effect wins out, and so there's an increase in precipitation in the monsoons. And I think this is quite a nice analysis of the CMIP5 models, one which is overdue and welcome.
Yeah, so a good point there. And yeah, of course, evapotranspiration does win out in the dry subtropics. But I mean, what I didn't mention is that some of the drying also does come from a movement in the Hadley cell, the poleward migration in the Hadley cell. So there's also some signal from that as well as the rainfall changes.
Questions? Julian, hand at the back there, and then gentleman at the back as the next question.
Julian Hunt. My colleagues in Southeast Asia are very emphatic that they now see this almost doubling of intensity of rain in peak events. I mean, from what used to be, all records were less than 100 millimetres per hour. Now they went up to 120, 150. Now it's 200 millimetres per hour. Of course, they're having to do practical things like dealing with these intense flooding events. And is this simply because we've got a deeper, stronger convection taking place? I mean, is that the explanation on a sort of local physics basis? Or are you trying to connect this into some larger scale? That doesn't seem to me so easy.
Yeah, so I mean, I agree that there is some observational evidence showing an increase in extreme precip above what we might expect from Clausius-Clapeyron. I think it's difficult looking at a point measure because you're affected by changes in circulation as well as the simple thermodynamic effects. There may be a contribution in some regions, such that you've got a shift in the monsoon slightly, a change in the aspect of the monsoon. But I think, yes, I mean, as far as I see, one of the biggest effects is simply the fact there's more moisture and it can invigorate storm systems, individual storm systems, and make them, the circulation actually increase in response and go above Clausius-Clapeyron.
But it's not very strong in the policymakers' report, I can tell you.
Well, Well, I think it's probably emphatic in terms of the amount of regions that are affected by a big increase in the intensity of rainfall, perhaps not so much in this difference between this big increase and the even bigger increase.
Thank you. And we have a gentleman at the back there.
Richard Lawson, I'm a blogger. I wonder if you could help me with an argument I was having with a denier recently, who pointed me to a paper which purported to show figures showing that the top of the troposphere specific humidity was going up, and it was therefore calculated this would retain more. The specific humidity was going down, and therefore he calculated that this would allow more radiation to go into space. I put this to ask Andrew Dessler for his help, and he said that in fact the moisture ratio, which I understand is relative humidity, was in fact going up, and this contradicted. But I'm still puzzled as to why specific humidity can go down, yet relative humidity can go up. If you could explain that a bit, please.
Yeah, good. I mean, good question. The evidence that I've seen, based on satellite data and radiosondes, is that actually the specific humidity is going up in the upper troposphere. Also, yeah, paper by Brian Soden you might want to look at, for example. They use two different channels, one sensitive to the specific humidity, one sensitive to the temperature, and they do show, again, that the specific humidity is going up. There is some reanalyses products that show specific humidity going down, but they're not reliable because there's a big changing observing system going into these. So overall, I would say that's not correct, that specific humidity is going up in the upper troposphere.
Thank you. More questions? David, at the front here, please.
Sorry, this may sound like a very simple question, and I hope I'm not the only person in the room thinking of it. But on your conclusions, you had that measurement of precipitation was still a big issue. You didn't really expand on that. Why is it so difficult when we have all of these climate stations measuring precip on land, presumably at least?
Okay, yeah, I probably oversold that in terms of over land. We're doing a lot better now, although there has been a big reduction in the number of observations of precipitation on land recently that go into, say, the GPCC record. I mean, Peter can correct me on that if I'm wrong, but